Chapter 1, The Way of the Program. The goal of this book is to teach you to think like a computer scientist. This way of thinking combines some of the best features of mathematics, engineering, and natural science. Like mathematicians, computer scientists use formal languages to denote ideas, specifically computations. Like engineers, they design things, assembling components into systems, and evaluating trade-offs among alternatives. Like scientists, they observe the behavior of complex systems, form hypotheses, and test predictions. The single most important skill for a computer scientist is problem solving. Problem solving means the ability to formulate problems, think creatively about solutions, and express a solution clearly and accurately. As it turns out, the process of learning to program is an excellent opportunity to practice problem-solving skills. That's why this chapter is called The Way of the Program. On one level, you will be learning to program, a useful skill by itself. On another level, you will use programming as a means to an end. As we go along, that end will become clearer. Section 1.1. The Python Programming Language. The programming language you will be learning is Python. Python is an example of a high-level language. Other high-level languages you might have heard of are C++, PHP, and Java. As you might infer from the name high-level language, there are also low-level languages, sometimes referred to as machine languages or assembly languages. Loosely speaking, computers can only execute programs written in low-level languages. Thus, programs written in high-level language have to be processed before they can run. This extra process takes some time, which is a small disadvantage of high-level languages. But the advantages are enormous. First, it is much easier to program in a high-level language. Programs written in a high-level language take less time to write, they are shorter and easier to read, and they are more likely to be correct. Second, high-level languages are portable, meaning they can run on different kinds of computers with few or no modifications. Low-level programs can run on only one kind of computer and have to be written to run on another. Due to these advantages, most all programs are written in high-level languages. Low-level languages are used only for a few specialized applications. Two kinds of programs process high-level languages into low-level languages: interpreters and compilers. An interpreter reads a high-level language program and executes it, meaning that it does what the program says. It processes the program a little at a time, alternately reading lines and performing computations. A compiler reads the program and translates it completely before the program starts running. In this case, the high-level program is called the source code, and the translated program is called the object code, or the executable. Once a program is compiled, you can execute it repeatedly without further translation. Many modern languages use both processes. They are first compiled into a lower-level language called bytecode, and then interpreted by a program called a virtual machine. Python uses both processes, but because of the way programmers interact with it, it is usually considered an interpreted language. There are two ways to use the Python interpreter: shell mode and script mode. In shell mode, you type Python statements into the Python shell, and the interpreter immediately prints the results. The first line of this example is the command that starts the Python interpreter at a Unix command prompt. The next three lines are messages from the interpreter. The fourth line starts with 3 angle brackets, which is the Python prompt. The interpreter uses the prompt to indicate that it is ready for instructions. We typed print 1 plus 1, and the interpreter replied 2. Alternatively, you can write a program in a file and use the interpreter to execute the contents of the file. Such a file is called a script. For example, we used a text editor to create a file named firstprogram.py with the following contents: print 1 plus 1. By convention, files that contain Python programs have names that end with .py for Python. To execute the program, we have to tell the interpreter the name of the script. These examples show Python being run from a Unix command line. In other development environments, the details of executing programs may differ. Also, most programs are more interesting than this one. The examples in this book use both the Python interpreter and scripts. You will be able to tell which is intended, since shell mode examples will always start with the Python prompt. Working in shell mode is convenient for testing short bits of code because you get immediate feedback. Think of it as a scratch paper used to help you work out problems. Anything longer than a few lines should be put into a script. Section 1.2. What is a program? A program is a sequence of instructions that specifies how to perform a computation. The computation might be something mathematical, such as solving a system of equations or finding the roots of a polynomial. But it can also be a symbolic computation, such as searching and replacing text in a document, or, strangely enough, compiling a program. The details look different in different languages, but a few basic instructions appear in just about every language. Input. Input will get data from the keyboard, a file, or some other device. Output. Output displays data on the screen or sends data to a file or another device. Math. Math is to perform basic mathematical operations like addition and multiplication. Conditional execution. Conditional execution will check for certain conditions and execute the appropriate sequence of statements. Repetition. Repetition is to perform some action repeatedly, usually with some variation. Believe it or not, that's pretty much all there is to it. Every program you've ever used, no matter how complicated, is made up of instructions that look more or less like these. Thus, we can describe programming as the process of breaking a large, complex task into smaller and smaller subtasks until the subtasks are simple enough to be performed with one of these basic instructions. That may be a little vague, but we will come back to this topic later when we talk about algorithms. Section 1.3. What is debugging? Programming is a complex process, and because it is done by human beings, it often leads to errors. For whimsical reasons, programming errors are called bugs, and the process of tracking them down and correcting them is called debugging. 3 kinds of errors can occur in a program: syntax errors, runtime errors, and semantic errors. It is useful to distinguish between them in order to track them down more quickly. Section 1.4. Syntax errors. Python can only execute a program if the program is syntactically correct. Otherwise, the process fails and returns an error message. Syntax refers to the structure of a program and the rules about the structure. For example, in English, a sentence must begin with a capital letter and end with a period. This sentence contains a syntax error. Can you see it? The T is not capitalized. So does this one. Ah, yes, there's no period at the end. For most readers, a few syntax errors are not a significant problem, which is why we can read the poetry of E. E. Cummings without spewing error messages. Python is not so forgiving. If there is a single syntax error anywhere in your program, Python will print an error message and quit, and you will not be able to run your program. During the first few weeks of your programming career, you will probably spend a lot of time tracking down syntax errors. As you gain experience, though, You will make fewer errors and find them faster. Section 1.5, Runtime Errors. The second type of error is a runtime error, so called because the error does not appear until you run the program. These errors are also called exceptions because they usually indicate that something exceptional and bad has happened. Runtime errors are rare in the simple programs you will see in the first few chapters, so it might be a little while before you encounter runtime errors. Section 1.6, Semantic Errors. The third type of error is the semantic error. If there is a semantic error in your program, it will run successfully in the sense that the computer will not generate any error messages, but it will not do the right thing. It will do something else. Specifically, it will do what you told it to do. The problem is that the program you wrote is not the program you wanted to write. The meaning of the program, its semantics, is wrong. Identifying semantic errors can be tricky because it requires you to work backward by looking at the output of the program and trying to figure out what it is doing. Section 1.7, Experimental Debugging. One of the most important skills you will acquire is debugging. Although it can be frustrating, debugging is one of the most intellectually rich, challenging, and interesting parts of programming. In some ways, debugging is like detective work. You are confronted with clues, and you have to infer the processes and events that led to the results you see. Debugging is also like an experimental science. Once you have an idea what is going wrong, you modify your program and try again. If your hypothesis was correct, then you can predict the result of your modification, and you can take a step closer to a working program. If your hypothesis was wrong, you have to come up with a new one. As Sherlock Holmes pointed out, when you have eliminated the impossible, whatever remains, however improbable, must be the truth. That's from Arthur Conan Doyle, The Sign of 4. For some people, programming and debugging are the same thing. That is, programming is the process of gradually debugging a program until it does what you want. The idea is that you should start with a program that does something and make small modifications, debugging them as you go, so that you always have a working program.